I'm going to start with a review of statistics and probability. I'm going to take this chance to remind you that these are the references that we have been using all semester during this class. So let's see what we covered in the first half of the semester. And presumably you have already got this down because we already had our midterm. All of you have already completed your midterm and resits, and all of your grades are final. Everyone knows what descriptive statistics is, hopefully. Course intro is like more of the motivation and what we are going to cover. Hopefully you guys have that covered already. We also looked at correlation. We also looked at statistical sampling, probabilities, and random variables. So you may ask, this is not going to come up again, right, in the end of the semester? Well, explicitly, no. However, if you take a look at this list, at least these things, these 4 things have come up again after the midterm. We studied more about, we studied again about correlation and regression, also descriptive statistics such as mean and variance, and all of that still comes into play. Probability, regression is a conditional probability, and random variables, especially the continuous ones were extensively talked about after the midterm. So although I can assure you that I will not make any questions explicitly about any topics before the midterm, it is still necessary for you to have these concepts, at least these 4 that I have highlighted here, down. So it is still relevant for you to complete your final exam. So having said that, allow me to repeat a little bit the materials from the beginning of the semester that I believe is still relevant and you need to know until the end. So this has a lot to do with just the video I showed you just now. So he did not explain it this scientifically, so to speak. In the video, they only said categorical and quantitative, if I recall correctly. However, even that can be described in a little bit more detail, starting from the nominal scale, which only has one criteria, which is mutual exclusivity. And that means that if one variable has one value, it will not have another one. This is valid for all scales. For the ordinal scale, we have an additional one, which is logical order. So there is an order to the categories. And the interval scale has the equal distance property. And finally, the most stringent one or the most precise one is the ratio scale, which shows that zero means absence. So among these, obviously, the ones that we have been computing in more detail, probably we're talking more about the interval scale and the ratio scale for a bunch of our computations. And also what is mentioned in the video, he also covered the population and sample. So hopefully that concept is clear to you by now. The population is everything, as he's mentioned. The sample is just a subset that we are studying. And the method in which we can obtain the sample, there are various methods, but in this class we covered 5 main methods, which are random, systematic, stratified, cluster, and convenience sampling. Hopefully you have this down as well, as you will need to do the sampling for your final project. Next, we talked about descriptive statistics. We described datasets, summarized datasets, and we also learned about standard scores. I'm going to repeat this because standard scores especially is very relevant to what we studied after the midterm. So for describing datasets, just like the video, it's like you're talking about whatever data you have. You are not making any conclusions yet. You're not inferring anything yet. You're just talking facts. What have I obtained from my sample? And usually we use humans are visual creatures, so we like to use graphs and bars and so forth in order to explain our data. Additionally, we can also describe our data or summarize our data in more simpler terms. Sometimes I don't need to know every single variable, every single value of the variable that we obtain. Instead, we can summarize the data set using these measures. Measures of central tendency tells you where most of the data is concentrated. Measures of variance tells you how far left and right, how is the range of values, and measures of position, which you can use to try to get an idea as to, oh, if I have a value, where do I stand in the distribution? Or the other way around, if I want to be in the top 5%, what value do I need to get? So these are the two things, percentile and percentile. Then after we have all of our values, just normal values, they can be in any range. You can have, you could measure a GPA, which is only the between 0 and 4. You could also measure height in millimeters, which would be between centimeters to millimeters, like thousands, right? So in order for us to be able to compare fairly between different types of variables and different, or maybe not necessarily different variables, but different scales and different types of distributions, we can map everything to a standard level or a standard score. That way it is easily comparable between two different distributions. Next, when we're talking about variables, sometimes we're not talking about a single one. So up until now, we're only talking about one single one at a time. But we can also use two or more to understand the relation, or in other words, correlation between the two. We can use a scatter plot to show visually how the relation is between the two. And we can also compute a certain, a certain coefficient to tell us about the actual strength of correlation, which we have already learned. There's Pearson R and Spearman Rho. Both of them compute more or less the same thing. And for the from the scatter plot, you can also infer linearity, strength, and so forth. Next, when we are talking about probability, we need to know these two terminologies, which is sample space and event. Sample space is whatever could happen, and event is a subset that actually could occur from the sample space. And in order to get our outcomes, we need to conduct some sort of experiment. Other words that are often used interchangeably in many problems is trials. So we have 20 trials, for example, we have 20 experiments, we have 20 chances, 20 times. So this is that's probably a hint when you read a question, like these words are usually used to explain the number of experiments or the number of potential outcomes that can happen. And based on the relationship between each event in a sample space, since we already know set theory, we can conclude some axioms or some rules that can be followed with the events, such as these on this slide here. I've tried to compile it into one slide to help you summarize the topics. So next, an easy assumption that you can usually take when you are conducting experiments. You can assume that it is usually assumed that every possible event has an equal likely probability. So to illustrate this, we assume that a die, like a dice, if you throw it, you have the same probability that 1 will come up and that will 6 will come up. So we assume that this die is not weighted, so it's fair, and that analogy should also apply to anything else. So every time you do an experiment, like if you throw a die, if you throw a coin, if you want to compute the probability of it raining, every event has an equally likely outcome. This is not actually valid in real life. However, this is a necessary assumption that we put in place in the context of statistical computation in order for us to have a manageable computation. And having established that, then we can compute the actual probabilities by finding out what events could actually happen. And usually when we're talking about these types of questions, we're not talking about a single event, however, combinations of events. And in order for us to know actually how many members are in that particular event, we can use the product rule, permutation, combination, circular permutation, or ring permutation in order for us to compute the actual number of possible outcomes. So just like when we were talking about variables, sometimes we're not handling only one variable. Sometimes we're handling more than one variable, and they are conditioning each other. So when I say that I'm computing a probability of event E given another event F, that means I'm putting F as a condition. F is the conditioning event. Due to that, my new sample space is F itself, because I assume that whatever it is, F must be valid. So F is my sample space. I'm not considering anything else outside of F, because if I'm going outside of F, that means F is not valid, and then my condition is no longer fulfilled. So that is how we can end up with this equation here. That will be a frequent occurrence in our computations, in our studies. It's this conditional probability right here. Based on the conditional probability, we also have the Bayesian theorem, or the Bayes theory, in which if I know the prior probabilities, what's the probability of a condition happening, and I also have a likelihood of what's the probability of A happening given a condition, then I can also compute the other way around. What is the probability of a condition happening based on the event A? And that gives me the Bayesian theorem, in which I can compute the opposite of what I know, the opposite probability of what I know. Next, I'm going to move on to random variables. These random variables we covered before the midterm. However, we did a lot of follow-up work on random variables after the midterm as well. So I believe that this is probably the shifting point from where I can actually make a question about it, and previously it's just as a note, at a just so you know basis. So from all of our experiments that we just talked about, I don't usually need to know actually every detail of what occurs from every experiment. However, sometimes I just need to know some sort of some sort of summary about what happens. Like instead of actually knowing what the dice has, if I have two dice, like the first one is 1 and the first one is 6, I don't need to know that. However, I may need to know a summary. What is the sum of these two dices? And in order to do that, I can just abstract that, take an abstraction of every single possible outcome instead of actually thinking about what came out. I don't need to know what came out. I can just map each equation to a certain number. So if I were talking about sums, this would be 7, this would be 4, and so forth. Please note that it is not actually a one-to-one relationship, because imagine if I had 1, 6 and 5, 2, both of them would be mapped to a single number, 7 in this case. And we already looked at the different ways that we can use to describe these probabilities of the values of random variables. I have covered these and reviewed these so many times. I do hope that you still remember it. So the first two can be used to describe discrete random variables, and the second two can be used to describe the continuous random variables. The first one tells me what is the probability of my random variable, large X, having a certain value x1. So what is the probability that my random variable X actually is that particular value, exactly that particular value, not less, not more, but that exact value. Next, we have the cumulative distribution function, which tells me the cumulative probability that my random variable X, large X, is up until X. So all of the probabilities, like what's the probability? It has all of these values up until X. And lastly, when I'm talking about the PDF or probability density function, I'm talking about what's the probability that my X, my random variable here, has a value between A and B. So anything between A and B. And these are the three functions that we need to know in order to define our random variable. And there are some special random variables as well that we studied in class. There are some discrete random variables and there are some continuous random variables. So the discrete ones we talked about before the midterm, so I will not ask anything that explicit about them in the final exam. However, as a review, let's remember the 5 discrete random variables that we already learned before the midterm. There is a Bernoulli, binomial, geometric, hypergeometric, and Poisson random variables. As an illustration, if I'm talking about the Bernoulli random variables, there are these types. I'm just asking yes or no. So there are only 2 possible outcomes, yes or no, success or not. And if I repeat this experiment and many times, then I have a binomial random variables. So I can compute how many times I get a yes. And I have the geometric ones to see how many times I need to do my trial until I get a yes. Hypergeometric talks about the unreplaced objects when I'm trying to take some objects. And the Poisson random variables tries to compute the amount of occurrences in a certain interval. So note here that everything here is discrete. I get a number out of each of them. But additionally, after the midterm, we talked about the special continuous random variables. So if here we only get a rounded number for every possible value of the random variable, we can also describe continuous random variables using some different distributions here. The first one is the uniform random variable, which, as its name suggests, is uniform in certain limits. So in this case, if I define a uniform random variable between the limits of A and B, that means between the values of A and B, I have an equal or a uniform probability that my random variable will have that value. Next, we also have the exponential random variables. So if we're talking about the Poisson one, just before, we're talking about, so in an hour, how many customers come to my store? When I'm talking about the exponential random variables, I'm talking about how long do I need to wait until the next customer comes. So I'm modeling the same problem. See, you realize here that we have the same information given to us, which is the rate, but we no longer have the interval because I'm not talking about a certain interval. I'm talking about how long until something actually happens. And lastly, but not least, arguably the most important, we have the normal random variables, which shape is like on the right hand here, which is also often called the bell curve or a Gaussian distribution. So this normal or Gaussian distribution is defined by the mean and the variance of this bell curve. But as you know, based on what mean I have and what variance I have, the shape of my bell curve can differ. Maybe it's over here. Maybe it's in the same place, but it's a little larger or higher. Maybe it's like that, maybe. So in order for us to avoid these misunderstandings, if I have different normal random variables, why not just change to the standard normal random variables? Just like in the beginning, when we talked about having different types of data, different ranges, different distributions, different variables, in order for us to make it comparable and make it a lot easier to compute, we can make standard scores. Just like that, even here, instead of having different normal distributions with different means and different variances, we can just try to map it to a standard normal variable with a mean 0 and a variance and standard deviation of 1. That actually helps us a lot because then we can assume that our distribution always looks like this. Always looks like this. I know that it will be centered at 0 and I know that the standard deviation and variance will be 1. That way, the proportion will never change. When I say that I draw a line here and this is like 0.05%, that will be valid for any variable as long as I map it to the standard normal random variable first. And here is the procedure of mapping a normal random variable, here with a random mu and a random variance. this is how I can change it to a standard normal random variable. I need to minus mean, divide by standard deviation, then I can put it back to a standard normal random variable, and I can use the CDF of a standard normal random variable, which is also denoted with a pi. And if this is fixed, I'm never going to change my graph, right? It looks like this. Then I can infer some things about it. We already learned that when I have a PDF, all of the sum of probabilities must equal 1. Here you go, it must equal 1. And I also know that the Gaussian distribution is symmetric. So if I need to compute that probability, I can use to my advantage both properties, and I can do 1 minus, or I can also compute the other side. Because since we know that everything is standard, the number never changes, and I can use a table. Remember, we can use a standard normal table, which I'm going to show briefly here. So here is our standard normal table, which will give you the exact value of probability or the area under the curve to the left, right? To the left, yeah, to the left of the line, or the left of the X critical point. So this one gives you the area to the left. So if you wanted to compute the area to the right, you can just do 1 minus, or you can do the opposite, or the symmetrical section of it. Remember, it is the CDF, or cumulative distribution function. That means it's everything up to. Remember, we already talked about that. So it's everything up to. So from the left up to that certain value there. Okay, so these are our standard normal random variables, right? And these standard normal random variables, they're standard. So everything I have, I can map it to the same graph, to the same distribution. Since they are all standardized and they're all following the same rule, then if I know that I have more than one normal random variable, I can start combining them, and I can end up with more normal random variables. As you can see here, we have a linear function of normal random variables, the sum of two independent normal random variables, linear combinations of the independent normal ones, and the average of independent normal random variables. So if I know N1 and N2, I could compute the average of them, and it would still be a normal random variable following a different distribution. In addition to the linear combinations of a normal random variable, we also have some different distributions that derive from the normal distribution, which are the chi-square, the F distribution, and T distribution. Note that every single one of these has a certain degree of freedom that will determine the shape of the distribution. So the skewness of the chi-square also is dependent on the degrees of freedom. If it changes, it might change like that, and so forth. So same goes for the F distribution. And for the T distribution, it doesn't change skewness because the T distribution is also symmetric. However, it'll change how wide it is and how high it is. Note that among these three, arguably, it is most important for you to understand the T distribution, because it is what is closest to the normal one. As you can see here, it's still symmetric. It's just not, doesn't have the same standard. It's still symmetric, and it's still zero. It can still be zero mean. So if anything, you must at least be able to master the T distribution, because both the Z distribution, which is the standard normal distribution, and the T distribution will be used for inferential statistics. Mentioning standard, while we're talking about the inferential statistics, we're about to start that right now. So now we have all our basics down. Let's see what we can infer about our population. So the main concept about inferential statistics is we only are able to study a sample, right? There's no way we can actually study the entire population. We only have the sample for us to study. So what can we infer about our population from the data we compiled from the sample only? In this course, we had two different things that we could try to infer, which is the probability distributions of the sample statistics or the explicit parameters of the population itself. Remember, statistics is to a sample what the parameters is to a population. So if I say mean of sample, I'm talking about a statistic. If I say mean of population, I'm talking about a parameter. And I can do these two things. First, we're going to talk about how to infer the probability distributions of the sample statistics. In order to do so, this is a theme here. In order to do any type of computation, we need some assumptions here. So we assume that although we don't know the population parameters, I don't know the mean of the population, I don't know the variance of the population. However, I am assuming that these parameters, this mean, this variance, has some sort of probability distribution. Call back to my random variables. So when I'm talking about a random variable, I know it has a probability distribution. I know that there is a certain probability that x equals 2. I know that there is a certain probability that x equals 3. And different values have different probabilities. So it could be more probable to have a value of x of 2 than of 3. If I assume that my mean or my parameter is some sort of random variable, then I know that it should have some sort of probability distribution. I don't know what it is yet, but it has some sort of probability distribution. Since I can't study the population, I'm going to study the sample instead. And I can assume that every time I take a mean of the sample, I take a statistic from the sample, then that is an independent random variable with that same distribution. I don't know what the distribution is yet. I just know that it's the same. So then if I were to take any sample data, any sample statistics, then I know that it would or it should give me an indication as to how the distribution of the population parameter is. And this is based on the central limit theorem. We already showed a video before in class, which I believe is a really good description, that we know that although we don't know the actual distribution, if I were to take the mean from different samples, it would follow more or less a normal distribution. So based on that assumption, the central limit theorem, I know that my data samples will follow some sort of distribution, right? I don't know what it is, but it has some expectation and it has a variance. And since I assume that I'm going to have a lot of different data samples, then I can assume that the sum of my data samples will be approximately normal with these parameters. So the parameters would be n times the mu of the mean of the mean of the sample, and n times the variance of the sample. This is the basis of the central limit theorem. Note that at this point, we only have considered the sum, right? This is not a statistic. Remember what statistics are. It's a mean, it's the variance, and so forth, right? The sum itself is not a statistic. However, isn't the sum only, isn't the mean a sum divided by the number of observations? And once again, we remembered when we were talking about the combinations of different normal variables, we knew that the linear combination of a normal random variable will be also a normal random variable. And thus, since I know that the sum here is normal, then if I were to multiply it by 1 over n or divide it by n, then it would also be able to be estimated as a normal random variable. So I can thus assume that the sample, when the sample size is large, that the x bar will also follow the normal distribution. As for the variance, it is a little bit more complex. However, I can conclude that the expected value of the sample variance is what I can compute, will also be equal to the population variance of sigma. So S is of the sample and sigma is of the population. So as I mentioned here, when I try to do some inference statistics, I first previously tried to infer the probability distributions. However, I could also estimate the parameters of populations explicitly. I want to actually know the value of the mean of the population. I want to know the mean of, I want to actually know the possible values that the mean could have. In order to do that, we need estimators from the sample, which is a statistic that we use as an estimator. And the type of interval estimates that I can compute are a little limited, arguably. Remember here that we have two types of estimates. I could give you a point estimate, and I could tell you, hey, the mean of the population is 3.1. However, if I give you only a point, 3.1, that opens me up to the possibility of being wrong because it's an estimation, right? I'm just estimating the mean of the population. So in order to give myself a little bit of leeway, I don't want to tell you the mean is 3.1, but I'll tell you that the mean is somewhere between 2.5 and 3.5. That way I give you an interval estimate and I have a little higher possibility to be right. So that's why we use interval estimates. So when you're trying to actually estimate the explicit values of the parameters, we don't, in this course, we don't try to give a point estimate, but we try to give an interval estimate. And the criteria is as follows. We can compute the confidence interval for a normal mean when the variance is known, normal mean when the variance is unknown, if I'm only talking about one normal population, or from two normal populations, I can try to compute the difference in means. And lastly, for the Bernoulli population, you can also compute the confidence interval of a mean. And here I have compiled the different limitations. So when the variance is known, we can use the Z table because we know that it is normal. But if I don't know it, I need to assume the T distribution because I cannot assume that it is normal. So as I mentioned previously, arguably from the derivations, you need to know about the T distribution the most. That is the normal mean when the variance is unknown, and the mean difference when the variance is known, mean difference when the variance is unknown but equal, and the mean for Bernoulli population. So basically, you need, as long as you know the concept, you just need to be able to find the correct equation for you to compute the correct confidence interval. Lastly, in our inferential statistics, we already covered that what we are trying to do when we're inferring from the sample to the population, we can do two things. We can infer the probability distribution of the sample statistics, or we can estimate the parameters explicitly. However, when we are making data-driven decisions, it's not usually actually necessary for us to actually have those exact values. But we need to know, we need to be able to disprove or prove a certain assumption or a certain hypothesis that we want to prove right or wrong. We don't need to actually explicitly estimate the exact value. So in that case, we can construct a test, a hypothesis testing scenario. And these are the terminologies that we need to know. The null hypothesis is the hypothesis of no difference. The alternative hypothesis is what is usually claimed, or what we are trying to, the research hypothesis, that's the correct term. And the test statistics is what we compute from the sample in order to make a conclusion about the hypothesis. We also talked about types of errors that can occur, as well as the level of significance, alpha, and the region of rejection. So these are the steps that we need to do when we are doing hypothesis testing. First, we need to actually state the hypothesis. You must always, always, always state the hypothesis before you start anything with hypothesis testing. Next, you need to set the criterion for rejecting H null, compute the test statistic, and figure out where it is. So these are the details. First, you need to try to define what are the hypotheses that you want to decide on. Then you need to set the criterion. What I mean here is like when you have the T or Z distribution, you need to know, you need to define this area here. Like this is called the rejection region. And you need to define this based on alpha. Remember our Z alphas here? You need to know like, where do I draw the line so that a proportion of my population is on the right-hand side. So here, for every line that you take in Z or T and alpha, then you can conclude this is your rejection region. Next, you need to compute your test statistic. Your test statistic is usually something computed based on your, I don't know it by heart, so please ignore it if it's incorrect, something like that perhaps. So this is perhaps your test statistic, and you compute it using the data you obtain from the sample. You can obviously compute the average, right? For example, and then you can try to find out where it is in your graph. Is it here or is it here? And depending on where it falls, you can either reject your H null or you do not reject your H null. Please be careful. When you say I do not reject H null, it does not equal accept H null. So please don't put an interpretation that, okay, so then we accept H null. No, it's not accepting, but you cannot reject. So you simply show that you have not enough, you don't have sufficient evidence to reject it. And this test statistic that you can compute in this step is based on what information you have. If you are testing one population, if you know your variance and if you don't know your variance, there are two different things that you can compute here. And when you are trying to do the hypothesis testing of two normal populations, you can try to estimate the difference of means, either when you know the variances or when you don't know the variances. And here are, I try to compile the tables to help you out. So if you're trying to test this one, that means you need to compute your test statistics as such, and you need to determine your region of rejection following that. And when you have two normal populations, this is your test statistics, and these are your rejection region. Note that a rule of thumb is that when you know the variance, use your Z table or normal table. If you don't know the variance, then you need to use the T table. And when I say variance is known and unknown, I'm talking about the population variance. Finally, we have our final topic. Once again, I'd like to assure you that this topic is a supplement to your material. So if I do release a question about correlation, it will most definitely be a bonus question. So when we study correlation in the front, we try to conduct or compute the correlation between two different variables. We have scatter plots to infer things about the relation, and you can compute it using the Pearson R. If previously in correlation, we say that X is correlated to Y, it does not necessarily show causation. However, with linear regression, we assume that one, in this case, usually the X, is an independent variable, which is the predictor, and Y is the outcome. So for a certain X value, I have a certain Y value, which can also be translated into conditional probabilities. What is the probability of Y given X? And since I'm only talking about linear regression, then I need to define this line using a linear or a line equation, which we can compute using least squares in linear algebra, which you've already covered in linear algebra. But in addition to that, so you can solve linear equation system as you know it, or you can also actually use some statistics. We can actually estimate the slope and the intercept using the covariance and variance of the two variables. And that brings us to the end of all of the statistic topics in a nutshell for the course of statistics and probability this semester.